Okay.
Have you not turned in English?
No, I turned in the last physics one.
Is that the only one? We've only had like 5 to do this semester.
We're gonna do so today. I want to cover. We can cover 29. Basically, going to cover 29 through 33. Might not literally do every single question, but we're definitely going to do 33, and we're going to do 29. So 29 says what, Aiden? What'd you say?
I got 2 classes mixed up.
Okay.
This one in calculus, so I just totally had like spring for
Okay, so you've got a solid disk that's free to rotate around this fixed axle. Okay.
Interesting.
And then we attach a 5 kilogram block. The disk is 20 kilograms, by the way. And let's get the radius in there. The radius is 0.4 meters. Okay, do I have all the information written there? Thumbs up?
Yeah.
The question's asking, what would be the acceleration of the system, basically? What's this guy's acceleration and what's this guy's angular acceleration when the block is released? So what's maybe a formula or two we could write down that are probably going to be useful?
That would that equals MA.
No.
That is. It's relevant.
So is that block like hanging or is that like touching the ground? It's hanging, so then
So like I'm holding it,
then
and then I let go of it, and the question is, it's actually a very complicated system if you just let it kind of be like a pendulum, if you think about it, but we're just going to say just right after you release it, how much acceleration do you expect? So some things to think about. What if you made the disk 2 million kilograms? What would the acceleration be pretty close to? 0, right? Because how's a 5 kilogram block going to exert enough torque to turn a 2 million kilogram disk, right?
Wouldn't you need MGH then? Like the amount of the block's gonna fall or like the energy it's gonna create. You can move the
You got a good point. This is actually a problem we're going to do later, where if we ask the question, how fast will this be rotating when this point of contact reaches that point, then you want to use an energy argument. But since we just want to know right at the moment of release, what's the acceleration going to be, then we just need to use Newton's laws. So Caleb's right that this is going to be relevant. And then what's the rotational version of this? Torque equals I alpha. So these are basically the same formula, but a little different. So, okay, we'll draw a force diagram. Well, and there's one more thing. What's the relationship between this guy's acceleration and this guy's angular acceleration?
They're the same.
Well, this guy's acceleration is the same as this point's acceleration because they're connected by a string. And if this point has acceleration A, you guys remember this? What's the relationship between the alpha and the A?
Talks about the radius, right?
Yeah. Acceleration equals
Alpha R.
alpha times R. So we're going to use this formula. This is going to, does that make sense? Why this is relevant?
Yeah.
Yes. So that's pretty key to understand that, yeah, this guy's A value and the disk's alpha value are related by this. Okay, so let's draw a force diagram for this block. Oh, by the way, let me mention this. Sorry. Here's a wrong approach. It's not obvious why it's wrong, but a wrong approach would be just to make this force be 49 newtons. Be like, oh, I'll say that the force here is 49 newtons because the block, the mg, is 49, and let's go 49 times the radius gives me the torque. I guess that's another formula that's necessary, right? Torque equals force times radius. Because the force the string exerts, right, the tension, we're going to multiply the tension in the string by the radius of the disk to get the torque. Does that make sense? Yeah. Okay. So, does anyone want to be brave and try to explain why can't you just say that this is 49 newtons? Huh?
It's freestanding.
True, because this is going to rotate. When would the tension in the string be 49?
When it's at the bottom.
True. Like let's say I was just holding the disk. Say I pinched the disk
So it's not moving.
and said, yeah, it's in static equilibrium.
Yeah.
Then it will be 49 newtons. But once you let it go, that's going to actually release some of the tension. So the tension is going to actually be less than 49, which makes the calculation more complicated. So, hope this. Maybe that's better. What, Colin? He was complaining.
Yeah.
That it was complicated.
Yeah.
It's not that bad.
I know.
Does this remind you of anything? The famous. What was that guy's name?
Atwood machine.
Atwood machine. Yeah, good. Okay, so let's draw the force diagram for the block. There is how many newtons pulling them down? 49 newtons pulling them down. mg. And then what are we going to call this vector? What letter do we usually use when it's a string? Capital T tension. Okay. And then how about at this point? Well, the rope is pulling down. From the disk's perspective, the tension is pulling down, right? But it's equal and opposite. Yeah?
Yeah.
Bruh. Okay. So which of these formulas can I use to talk about this little system here, this little F net equals ma? So I can say, well, using this formula, the net force is 49 minus the tension. So I'm using F net equals ma. The mass is 5. And the acceleration is, what did you like to know? That's what we're trying to figure out, right?
Yes.
Acceleration. 2 variables, tension and acceleration. Hopefully this is ringing a bell. We've done this before, this kind of thing. We need one more equation. So let's now write the equation for this part of the system, the disk. Which of these formulas should I, well, I guess it's kind of up for debate which one we start with.
T equals I alpha.
Yeah, let's start with the torque equals I alpha. So you're going to go torque on the disk is equal to the disk's I value times the disk's alpha value, right? Now, what this will be not super easy question to answer, but what am I going to do with that guy? What should we do with that? Well, it's a simple answer, but it's not obvious.
It's not 49 times 0.4.
Very close. Look over here, and then look here. The torque on the disk is the force on the disk multiplied by the radius at which the force is applied. What's the force being exerted on the disk? T, the tension. What's the radius of the disk? 0.4. So my torque is the tension multiplied by 0.4. Are we fine with that? Okay. What's the I value for the disk? It doesn't say it on this problem, but if you look to the previous problem, 28, for a solid cylinder, which a disk is a cylinder, it's 1/2 times the mass times the radius squared. Does everyone understand that? So I use this idea. For a I for a solid disk is 1/2 mr squared.
I didn't realize those were set for different objects. I thought it was just in this instance.
Well, I gotta show you guys
or whatever.
You thought, wait, what?
I thought it was just like whatever the question was. It was okay. This one's 2/5 mr squared. This one's 1/2 mr squared.
Oh no, you start if you use this is the general idea. You go the I value of any object is the sum of all the mr squared values over that whole object. Now if it's a smooth object, you would actually do an integral of mr squared. The triple integral, if you're wondering, if you calculus people, it's a volume integral. You volumetrically integrate over the.
Would it be 5 or 20? The disk is 20.
Oh, thanks. Yeah, I messed that up. Thanks. Yeah, you guys hear that? That's wrong. It's the mass of the disk, not the mass of some other thing that doesn't matter. Or no, it matters, but certainly you get why the block doesn't affect the I value for the disk. Thanks, Caleb.
Facts and logic.
Facts and logic.
Smart moments.
And then there's one more part to this. What do you think I'm going to replace the alpha with? A
divided by R.
A over R. A divided by 0.4. That was a lot of substitutions all at once. So if you were able to follow that, that's good. Here, look, I looked up list of moments of inertia. So yeah, like different objects, like any solid cylinder, the moment of inertia would be 1/2 of its total mass times its radius squared, assuming uniform density. So, wait, I gotta make it smaller. So there you go. There's your point mass. There's 2 point masses. There's a thin rod. And then for the thin rod, it depends on where's the center of rotation. So for a thin rod rotating around the center, it's this. But if it's rotating around one of its ends, it's this. Where's some interesting ones? There's your solid disk. Where's some good ones? A tetrahedron, an octahedron. What's really interesting is an octahedron has a really simple formula. It's just like for a solid octahedron, it's 1/10 of ms squared, where s is the side length. But spheres are also pretty simple. They're just some factor multiplied by mr squared. Where's some weird ones? Cones are pretty weird. Here's a torus. Someone actually sat down and did all the math on this. Torus. Here's a rectangular, like a sheet of metal, would be this. I don't know, very interesting. Oh, here's one. A rectangular box, but where it's rotating around a diagonal. Is this.
Something like calculus.
And then here's one, another rectangular box, but it's rotating like around a vertical axis, but it's tilted while it's rotating. It's this weird thing. So anyway, hopefully that makes sense.
Infinite disk?
An infinite disk with mass distributed in a bivariate Gaussian distribution on 2 axes around the axis of rotation with mass density as a function of the position vector x. It's pretty simple, guys. Just simple economics. Guys. Just simple economics. No, that's a 2-dimensional. You guys know the normal curve.
Oh yeah.
Where you go, oh, how heavy is an NBA player? And you graph. You go, oh, usually it's going to follow some kind of distribution where like this is like the average, and then some of them are really heavy, and some of them are not very heavy. Shaquille O'Neal, Spud Webb, you know, that kind of thing. You must have seen this before.
Yeah. It's something up.
It's one of the big. Well, it's not 1 over x squared plus 1, but it's related. It's related. It's related to e to the. It's proportional to e to the negative x squared. There's a whole bunch of there's a big factor in front of it, but yeah, I hope. I mean, if you never saw that in any of your like earlier math classes, that's a problem. You certainly, if you take statistics, you'll learn all the details. But I mean, the basic idea. If you take, there's a lot of data you could take that'll follow a normal distribution. You graph it. I don't know if I'm making any sense. Never mind, just forget it. Okay, sorry. Let's finish solving the question. So I got one equation. This equation is very tidy. He's already pretty tidy. This guy, we need to tidy him up. What do we notice? I mean, I have t times 0.4 equals 10 times, now if you have 0.4 squared divided by 0.4, how many 0.4s are left? 0.4. Or there's 1.4 left, I should say. Does that make sense?
Oh, yeah.
Isn't it then 10 times?
And then the 0.4s cancel out. Long story short, you get tension equals 10A. That's interesting. You feel me?
Mhm.
So what can I do with that? Plug it in. Do a substitution. Got to combine the two equations. I have two variables and I have two equations, so we should be good to go. So this now reads 49 minus 10A equals 5A. So 15A equals 49. So what do we get there?
3.27.
Okay.
It's really 3.26.
Oh, that's okay. Close enough for government work, as Michael Jacobs would say. All right.
Are we done?
Well, the question also asks one other question,
Angular.
which is pretty easy, right? Yeah. So that's the acceleration of this block. It's also the acceleration of this point, linear acceleration. So then, therefore, what's the angular acceleration of the disk? It's just the A divided by the R. What do you get if you divide that by 0.4? Seven-ish? 6 point something? 7 point?
8.18.
Goodness. 8.18 what?
Radians per second squared.
Radians per second per second. Radians per second squared. Three thumbs up? Are we classy, bougie, ratchet? We're okay with that? No problems? No problems? Okay, let's, I want to make sure we get to the last question, so if we have time, we can double back, but the question after this one, number 30, is really similar. It's just you're not, instead of numbers, you're going to have like a, I can't remember if it's like a big M or a little m, or it's like what we've been doing all year. You're going to basically derive a formula. Bear in mind the number 30, it's not a solid disk. It's a hollow ring. So it's not 1/2 mr squared, it's just mr squared. Right, Trenton?
Right.
Trenton, try to contain your excitement, bro.
You said it's just MR squared?
Yeah, for a solid, for a ring, for a hollow ring. It's mr squared. What?
33, correct?
That's what we're doing, 33.
Okay.
I still just want to hear Trenton's a cappella Star Spangled Banner in multiple keys.
Yeah. Or start on.
I lost my thing, but I know what it says. It says that we want, so. Oh, I gotta show you something. I almost forgot, man. Taylor, you watch it. I think that's what?
Using a doodad.
I found it. You guys are gonna need a burrito. Oh boy. What did I come to rant?
Oh my god.
We're gonna do a race.
A race?
It's only the best question you can ever ask in physics, which is who will win? Who will win? Ugh. Speaking of which, I was getting bigly triggered on that TV show because you guys have seen those Avenger movies, right?
Oh, yes.
You watch this Wanda show, and it's like, okay, obviously she could have just killed all the bad guys anytime she wanted. Same thing with Captain Marvel. Why do they create these heroes that are like 1 trillion times more powerful than all the other heroes? And then in hindsight, you go, well, why don't they just wipe out all the bad guys with like a single pew?
We all want there.
It is the ultimate question.
The ultimate question to life, the universe, and everything. Why didn't Captain Marvel just destroy Thanos and his entire army? She could have easily done it. I didn't realize Wanda could have as well. She could have easily done it. No?
It's a wonder.
Well, yeah, Wanda was busy.
She was busy? What was she busy with?
Reading.
Isn't that what Captain Marvel actually says in the movie? She goes, sorry, I was busy with other stuff. Isn't this guy going to kill half the universe? What's more pressing than that? Oh, whatever. Anyway.
She was busy, huh?
She was busy.
She's got things to do.
She was just busy.
Just because she can doesn't mean she
She was built different.
She's
Okay, sorry, I was unprepared, but this is important.
You didn't ask for all that responsibility.
True.
She just wanted to go down.
Yeah. That's why I like, Thor. Thor just had ennui. He was like, I don't wanna. He had a big belly. That movie. Remember what I'm talking about? He was living the good life, exactly. He was living my dream existence. Okay. Okay, guys, sorry.
It's time.
Huh?
Is time the witness history.
Time is a flat circle, Winslow. Okay. I need to. Oh, and then this one's for all the millions of Twitch fans out there. Hello, Julia. You are now the caretaker of this thing.
Is it for circuit?
Man, the production values on this show are getting really good.
Yeah, moving parts.
Sorry, Leap and Lemurs, you're gonna have to take one for the team here. All right, here we go. Who's gonna win the game? Who will win? Who will win? Who will win? I'm gonna race
The
them.
hollow.
They're
The
gonna
hollow.
tie the disc. I don't know.
The one with more
The chunkier one.
Yeah, I'm gonna go with the
Bigger
block.
boy.
The disco. The
Thick.
solid.
I gotta make sure I release them at the same time. Okay. Who will win? Will it be close? Let's see. Ready, spaghetti, go. Oh, lemurs. Okay, I got it, right? Who won? It was a very clear victory.
The solid.
This guy won, okay? Now, we're going to get into the bigger details of this later, but these actually are the same mass, if you're wondering, the same weight.
Oh.
Now, here's the thing, though. I mean, how many problems have we done involving, like, blocks sliding down ramps and stuff? A lot.
200.
How often does the mass of the block matter how fast the block goes down the ramp?
Never.
It never does.
Somehow.
So let's see, for a rolling object, I don't know, maybe somehow now the mass matters, maybe not, but like, I hope your guess would be at this point in the class that the mass can't really matter, right? We're going to prove that in a second, but. So what does matter? The mass doesn't matter, but.
The air resistance.
No. Theirs is negligible for how slow they're moving and stuff.
Center. Who's the torque?
Close. They both have the same center of mass. The center of mass is in the
yeah.
center for both.
To distribute, like,
Oh.
the mass distributes
Oh,
throughout the circle.
Yeah, the distribution of mass.
There
What?
we go.
Okay, so here's the thing. What's the I value for this?
MR squared.
1/2 mr squared. Half of mr squared. This guy has an I value of mr squared. So who rolls more? Who spins more easily?
1/2 MR squared.
Zach, you catching all this? I'm kind of explaining all the big ideas here so you can understand it. Okay. This guy spins more easily. He has a smaller I value relative to his own mass. So who's going to have an easier time getting rolling?
The one with
This guy. And thus he will have a bigger acceleration. Okay. So what you want to look at when you want to say who's going to roll faster down a ramp, it's whose I value suggests that he's going to be more easily spun, more easily accelerated. Does that make sense?
Yeah.
So here's a quick little check to see if you got it. I'm just going to make up two objects. Well, I guess, no. Oh, no. Okay, sorry. On that problem number, what's the one right before it where it's asking it says don't do any calculation. 32 says don't do any calculation. So who would win in a race between a solid sphere and, say, a solid disk? Solid sphere, right? Because what's the solid sphere? The I value for a solid sphere is 2/5 mr squared, and the I value for a solid cylinder is 1/2 mr squared. Well, who's bigger? This guy has a bigger coefficient there, so he's going to be a little bit more resistant to getting spun, okay, than him. So here, I'll show you one more, since everyone's always thinking a really common answer to these questions is, oh, the heavier object is going to roll faster. Well, this one's much heavier than this. This is a full kilogram. So I'll race these two. So a tie. And that's because, why is it a tie? This guy's a smaller radius. He's way heavier. Well, they both have the same I value formula. Sure, this guy has a bigger M and a smaller R, so they probably have different actual I values, but relative to their mass and radius, it's that 1/2 amount. So, okay, let's do the calculation. This question has a beautiful answer. One of the things that I think makes physics kind of just nice and tidy. So, last question says, if you've got a round object, okay, it gives us a hint. It says, just call the I value of this thing K mr squared. Now, do you see why we're doing that? What's K for a solid cylinder? 1/2. What's K if you're a solid sphere? 2/5. What's K if you're a hollow sphere? 2/3, right? So we're just generalizing this. We're going to do the calculation only one time using this K, and at the very end say, well, what's the answer if K is 1/2? What's the answer if K is 1? What's the answer if K is 2/3? Get the idea? So the question is, let's ask this. What's the acceleration for a frictionless block? This is theta.
mg sine theta.
Close, that's the force. The acceleration we know is g times sine of theta, where g is 9.8 meters per second squared. Right?
Yeah.
Let's just, sorry. Oh my God. I can't move this thing without knocking the camera over. Okay, there we go. That's better. All right, so that's a hint that this answer is going to probably be connected to this answer in some way. Because there's a difference between a rolling roly-poly and a sliding block, but they're still fundamentally the same thing. It's gravity causing a thing to go down a ramp. So, okay, so what's going on here? Well, I know that, let's use what Caleb just said. I know that for the same exact reasons we've talked about before, there's a force pushing him down the ramp. The size of that is mg sine of theta. You feel okay about that? That's a force. mg sine of theta.
Wow.
What's he talking about?
Isn't it modern world history?
Well, we must be on the World War I unit.
Okay, now there's another force that's opposing. If that's all that was happening, what would the answer to the question be?
Mg sine theta. You can say,
No.
oh, Mg sine theta.
So you'd say this equals MA, the M's would cancel out, and you'd have this answer. So there must be something else. Well, what's this force that's hint? It's located right there, and it points that way. What's that called? Friction. You can't roll without friction, right? Like, who's providing the torque to roll the thing? Well, it's got to be friction, right? Who else is going to do it? Make sense? It's like when you slide a bowling ball. If the floor is nice and slippery, then sometimes the ball doesn't even spin, right? Or it spins backward. Versus if you roll a basketball down a basketball court, it rolls without slipping because of that friction, right? What?
I like the
I like
I've
that.
never gotten well.
Okay, this is the friction force then. Now, here's the thing. This is where it gets a little confusing. Some people go, well, I'm just going to go friction force equals mu times normal force. You can't do that. It's not this kind of friction. It's not kinetic friction. It's actually static friction. Because the ball, if you looked at the interaction between the ball and the surface, they're not actually sliding against each other. They're actually just in contact. So it's actually static friction. And if you recall, static friction just involves an inequality. You can't get a nice equation there. So we got to be a little bit more clever here. Now, here's the trick. This is the only force that's exerting a torque on the ball. So I can write torque equals I alpha. All right. Now, what's the torque? The torque, very good. It's the force times the radius. So I go friction force times the radius. That makes sense?
Mhm.
The I value is kmr squared. And the alpha value, who remembers this one? Is A over R. Okay. Hannah just says go to pick up something at the office between classes. All right.
So maybe
Who, me or Hannah?
we need to go say hi to the office ladies. They're so nice.
So what's R squared divided by R on this side? Just R. And then what happens?
First cancel again.
The R's cancel out, and you get this really nice expression for the friction force. K times the mass times the acceleration. Okay, now we need to use that. We haven't used this yet, have we? So if I want to write the big famous formula, F net equals ma, this is what we always use when we're trying to figure out the acceleration for a frictionless block or even a frictiony block on a ramp. What's the net force according to this diagram? Yep, it's mg sine theta minus that friction force is equal to the mass times the acceleration. And then what do I do? You see what I'm talking about? Nice little substitution there. So I got mg sine theta minus kma equals ma. What's something you notice?
Mass.
All those masses are going to cancel out. It's the same m all the way through. It's the mass of the object. Now what? What can you do?
You could simplify that from adding.
I have a Ka here. I'm ultimately trying to solve for A, right? And I got two A's. That's not great. So get them together. So add this to that side. Like that. And then what? Close. No, I have two A's still. I don't like having two. I want to have one. Factor it out. Very good. Factor out the A. What's left over?
A1 plus.
1 plus K. And then we're done. Look at that answer. That is beautiful. If you can't appreciate the elegance of that, then physics might not be a field for you. That's lovely. Look at that.
Yeah.
It's so similar to this, just an extra 1 plus K factor. So what happens? Let's last couple remarks here. So what's the K value for a frictionless block then? Something that doesn't even need to rotate. What's the K value? 0, right? Okay, what happens? Let's say then so let's do one example. Let's use the solid sphere. What's going to be the acceleration for a solid sphere rolling down? Just realized it says it not anywhere. Okay, sorry. So, was it said the angle side theorem. So not a valid theorem. The acceleration for a solid sphere, then what am I going to plug in for K for a solid sphere? 2/5. So let's see what happens. I'd have 1 plus 2/5. So what's 1 plus 2/5? 7/5. And dividing by 7/5 is the same as multiplying by 5/7.
Yes.
So what you can say here is that, sorry, Twitch friends. Okay, sorry. What you can say is, so how does the acceleration of a solid sphere compare to a frictionless block?
That's the relation.
It's 5/7 as big. So what is that as a percent? Like 72% or something? 70%? Maybe. Let's see. 71. So a solid sphere will accelerate roughly 71% as fast as a frictionless block. Okay. And then same, you can perform the calculation for all the other ones. So there you go. Sorry for the torture.
Interesting.